Hello, mathematicians. Asia Pranks here from Skew the Script. Today, we'll be looking at costs and emissions related to Tesla electric cars. We're not going to be talking about Elon Musk, but we will focus on whether or not expensive Teslas are worth the price tag. Let's skew it. Even though Teslas are electric, some electric grids are powered by coal. Emissions from mines are used for battery materials, and there are other hidden costs and emissions we need to consider. That's a lot to think about. So for today's key analysis, we will answer the question, can electric cars beat the cost or even the environmental impact of gas cars? You can follow along using the notes linked here and in the description box. FYI, there's actually another version of this lesson in the New York Times if you want to check that out. So there's 3 math topics that we're going to explore to understand if electric cars are better. And we're going to start with constructing a system of equations. So, should we buy an electric car? Teslas are expensive, but they may pay off over time because they require no gas and less maintenance. But at what point is buying a Tesla worth it? First off, let's think about upfront costs. You can save over $8,000 by buying a car like a Camry or a Honda instead of an electric Tesla. But what about the costs after that? When you own a car, you also have to pay for fuel or electricity, maintenance, insurance, taxes, and possibly state inspections. To zero in on some of these costs, let's think of a scenario comparing the Tesla to a Camry. Imagine each car's lifetime is 12 years, and you own the car for all 12 years. Which car will end up being cheaper overall? To answer this, we'll need some data. And lucky for us, MIT has compiled a whole data set of car costs and emissions. For this scenario, we'll assume typical US gas and utility prices, driving distance, maintenance, and electric grid efficiency. We'll track the costs and emissions at every step. So as I mentioned before, here are the upfront costs for each car. Clearly, the Camry wins this round. Now, based on MIT's data, this is the typical yearly cost of gas or electricity and maintenance for each car. Looks like Tesla's going to win this round. So let's create linear equations to model the total cost of each car over time. We'll let Y be the total cost and X be the years we've owned the car. So for our electric car, let's start with representing the total cost. Our upfront cost is $37,990 plus our yearly cost of $1,016. Multiply that by X, which represents our years. We're going to rearrange our equation so that it's in slope-intercept form, and this is our linear model. Pause the video and see if you can create the model for the Camry. So here's our initial equation with the upfront cost and the yearly cost multiplied by X. We're going to rearrange this equation, and bam, this is our linear model for the Camry. Okay, now that we have both models, let's think about owning the cars for 12 years. Which car will be cheaper overall? To answer that, we need to change the X in our model to 12. Let's start with the Tesla. We're going to substitute in 12 for X, and after doing some quick calculations, we get $50,182. That's the total cost for the Tesla. Pause the video and calculate the cost for the Camry. Once again, we're going to plug in 12 for X. And after some calculations, we see that the cost of the Camry is $54,326. So the Tesla wins. The Tesla is cheaper over 12 years. In 12 years, the Camry is actually $4,000 more than the Tesla. The 2 equations we just wrote can be considered as a system of equations. Let's see what happens when we examine our system with a table or a graph. As we compare the Tesla and Camry, it might be helpful to know how long we need to own the Tesla for it to pay off or end up being cheaper than the Camry. Let's try and answer this question using a table. We'll find the total cost for years 0 to 10 for each car. Let's start with year 0. We find this by plugging in 0 for X. And when we do this, we get our initial car prices. That makes sense because we plugged in 0 for X. Now let's find the cost after 1 year. We plug in 1 for both of the X's, and there's our cost after year 1. For the Tesla, the cost increases by $1,016 each year. Here's what that looks like in our table. For our Camry, the cost increases by $2,038 each year. Here's what it looks like in our table. Now, the question is, at what year does the Tesla become less expensive? Pause the video and find that year. It looks like at year 8, the Tesla is cheaper to own than the Camry. Let's see if the graph provides us with any additional information. Here we have the two models graphed together. The x-axis shows the year of car ownership, and the y-axis shows the total cost of owning the car. Which graphical feature shows you the initial car costs? And which car initially costs more? Pause the video and try answering these questions on your own. The y-intercept is the graphical feature that shows us initial costs. It's the cost at year 0. This is where the line crosses the y-axis. And looking at the graph, the Tesla has higher initial costs. Now think about which graphical feature shows you the yearly car costs. Which car costs more per year? Pause the video to answer these questions. The steepness of the line or the slope shows the yearly costs. The Camry has a steeper line. This means it has a larger slope. It costs more per year than the Tesla, as we saw earlier. Now I want you to think about which graphical feature shows you when the Camry begins to cost more than the Tesla. At year 0, we see that the Camry is catching up, and it intersects with the Tesla line right here. This intersection shows us when the Camry becomes more expensive. It looks like it occurs just before year 8. So by the time you've had the car for 8 years, the Tesla is cheaper. The last thing we're going to do in this video is solve a system of equations using substitution and elimination. So far, we've seen that over time, electric cars can save you lots of money. But are they better for the planet? Now let's consider where the electricity for these cars is coming from. Some electric grids are powered by coal, and the mines used for battery materials produce emissions. So is having an electric car actually better for the environment? That same MIT data source has emission information at every step. Mining for materials, producing the car, driving the car, creating emissions to produce electricity in the grid, and so on. Let's start by focusing on the emissions needed to produce cars. Making a Tesla produces emissions equivalent to the global warming potential of 11,074 kilograms of CO2, whereas the Camry only requires 7,402 kilograms of CO2. So the Camry is greener to produce. But which produces fewer emissions over time? We don't just care which is greener to make. We want to know which one is greener to own and drive. So for electric cars, emissions come from coal-powered electric grids. And for gas cars, emissions come from burning and refining gas. We saw that the CO2 required to produce the car is less for the Camry. But when we look at the yearly CO2, the Tesla is much better. So just like we made equations for owning each car, we're now going to make equations for the car's total emissions during the years of ownership. This time, Y will represent the total emissions instead of the total cost. For each equation, we have the initial amount of CO2 required to make the cars, and we're adding on the emissions per year. Now that we have both equations, we can graph them. Graphing is going to help us to visualize the difference between the two cars. Examine the graph and try to determine when the Tesla becomes more environmentally friendly. It looks like this is the intersection of the two lines. So after the first year, the Tesla becomes more environmentally friendly. Eyeballing the graph gives us an approximate answer. But can we figure out exactly when the Tesla will become more environmentally friendly? You know we can, and we're going to use algebra to figure this out. Our goal is to find the exact point of intersection. The intersection occurs when both equations y value and x value are equal. So let's go back to our equations. And we're going to solve using substitution. Since the point of intersection occurs when the y value and x value are equal, we can substitute the y's or x's between the equations. So I'm going to take all of this from the Tesla equation, and I'm going to substitute it in for the y in the other equation, like so. Now I have an equation with a single variable, so I can solve for x. First, I'm going to subtract 7,402 from both sides. And now I'm going to subtract 1,368x from both sides. That gets us to this point. I'm now going to divide both sides by 3,157 because I want to isolate my x. Dividing by 3,157 on both sides leaves us with the value of x, which is 1.16. Let's figure out what this 1.16 means in the context of the problem. This value of 1.16 can be seen here, and this means that the Tesla becomes environmentally friendly after 1.16 years of driving. This is about 1 year and 2 months. We might also wonder, what are the total emissions when these two lines cross? That means we're looking for the y value when x is equal to 1.16. So returning back to our equations, we can plug in 1.16 in for x into either equation. I'm going to use the equation for the Camry and plug in 1.16 for x. After simplifying, I can solve for y. I get that y is equal to 12,651 kilograms of CO2 emissions. Okay, there's actually another way to solve this system of equations. We just use substitution. Now we're going to use elimination. Once again, remember that the y value and the x value are equal at the point of intersection. So when we use elimination, we're going to subtract our equations. Since our y variables have the same coefficient, they can be eliminated. So here, y minus y equals 0. The other two terms are going to be subtracted as well because they're like terms. Now we're left with this equation with one single x that we can finish solving. So in this case, I'm going to add 3,157x to both sides so that my coefficient for my x variable is positive. Then I'm going to divide both sides by 3,157. Here I get x is equal to 1.16. This is the same x value we got when we used substitution. We get the same value because we're just using a different method for solving. Time for a quick discussion. In certain situations, buying a gas or hybrid car could be more environmentally friendly than buying an electric car. Pause the video to think of a situation in which this is the case. There's a lot to consider when buying a new car. Hopefully you learned something in this video that could help you with purchasing a car one day. Thanks for watching. The steepness of the line or the slope, Asia? Okay.